When high-stakes machine learning models fail in production, the average remediation cost hits $1.8 million per incident. Automated machine learning, or AutoML, is engineered to strip away development bottlenecks. It automates data preparation, feature engineering, and model selection, optimizing the entire pipeline for raw velocity. Unconstrained velocity amplifies systematic risks. We see this most clearly in automated feature selection, which aggressively explores proxy variables and exaggerates historical biases far beyond manual engineering. Once deployed, these models suffer from silent performance degradation. They bypass traditional monitoring systems that track latency and error rates, masking the actual governance failures occurring underneath. There is a severe disconnect between policy and practice. Today, 95% of organizations claim to have responsible AI commitments. Yet almost none actually integrate automated fairness constraints or audit trails into their production MLOps stacks. The industry assumes this is a human problem. The prevailing myth is that solving AI governance requires better ethics training and highly experienced data scientists. Recent empirical data from a 220 practitioner survey completely refutes this idea. Comparing years of ML experience against governance implementation shows a completely random distribution. Individual practitioner experience has zero statistical effect. But shifting the axis to organizational maturity reveals a tight ascending correlation. Formalized processes and tooling actually dictate successful adoption. AI governance is an engineering pipeline problem, not an individual competency issue. Relying on the ethical intuition of a developer will fail. The pipeline itself must enforce the rules. To build the pipeline, we first look at the baseline standard for MLOps, the traditional human-in-the-loop model. This diagram illustrates that in a human-in-the-loop system, human intelligence acts as a toll booth. A practitioner must manually intercept and approve individual decisions as they happen in real time. Applying this to an automated system introduces a severe structural failure point known as the scalability paradox. As AutoML increases the sheer velocity of model generation, requiring real-time human intervention becomes a massive, crippling operational bottleneck. The need for governance intensifies exactly as the system outpaces our capacity to monitor it. The solution is to restructure the pipeline using a human-on-the-loop architecture. Human-on-the-loop entirely removes human expertise from real-time decision interception. There are no manual approvals holding up the active training process. Instead, human intelligence is repositioned to the boundaries. First, at the beginning of the pipeline, where practitioners specify ex-ante constraints, defining the exact fairness thresholds and risk budgets before a single model trains. Second, at the end of the pipeline, humans conduct ex-post outcome auditing by reviewing standardized compliance dashboards and explanation logs. By defining the rules up front and auditing the receipts at the end, the automated pipeline in the center is free to run at maximum velocity without sacrificing oversight. Governance transitions from an interruptive roadblock into a structural property of the system, one that scales infinitely alongside AutoML. Executing this requires the principle of shift left. This mandates that we apply quality constraints at the earliest possible point of intervention, data ingestion. This happens in phase 1 of the pipeline, data preparation, relying heavily on ex-ante data contracts. Before data ever enters the pipeline, humans define YAML contracts that enforce strict schema constraints and type checking. If the data doesn't match the contract, the pipeline automatically rejects it. This single automated check prevents the undetected data cascades responsible for half of all documented production failures. As the pipeline moves into phase 2, feature engineering, the risks shift. Left unchecked, AutoML algorithms will ruthlessly synthesize proxy variables to extract information about protected attributes, even if explicitly removed. We counter this with the adversarial feature audit. The pipeline routes new features into a red team classifier, which attempts to predict protected attributes from the data. If its accuracy exceeds 0.70, the feature set is automatically rejected. This ensures the model cannot illegally reconstruct restricted demographic data through complex proxies. By encoding these mathematical limits directly into the continuous integration flow, fairness becomes a non-negotiable engineering constraint rather than a post-training debate. Implementing these constraints introduces pipeline friction, but not all models carry the same societal weight. We do not need maximum governance overhead for every deployment. We regulate friction using the frame risk scoring system, multiplying data sensitivity, application criticality, and harm severity. A Tier 1 application outputs a low score, triggering only Phase 1 contracts, but a Tier 4 high-risk model activates the full suite of pipeline controls. Despite these available controls, the empirical data highlights an alarming reality. The largest implementation gaps exist exactly where the risk is highest: Phase 4, production. 3 critical production controls are almost universally missing. First is async explainability, which requires generating fast approximations for real-time inference, backed up by deep explanations for nightly batch audits. Second is automated rollbacks. The pipeline must be configured to instantly revert to a previous model state if demographic parity degrades by more than 5% in live production. Third is the integration of governance gates, codified directly into the CI/CD pipeline, designed to automatically block deployment if cryptographic artifact lineage fails verification. Failing to automate these Phase 4 controls invites severe regulatory fines and user harm exactly when the model hits the real world. Relying on the ethical intuition of individual practitioners consistently fails at production scale. The human-on-the-loop pipeline operates as a continuous 4-phase system. Human expertise establishes the risk budgets, constraints, and fairness limits before automation begins. The system generates the model, and humans return to audit the standardized compliance dashboards and explanation logs. This architecture perfectly decouples governance scalability from human intervention throughput. To close the documented 1.69 Likert point implementation gap, organizations must aggressively shift their resource allocation. Investments must pivot away from individualized data science training programs. True responsible AI demands engineering structural capabilities, prioritizing cross-functional coordination, and enforcing rigorous policy as code directly within the CI/CD pipeline.